Vice President.
Hello everyone, welcome to Bileşik Algebra and Number Theory Seminar. It's my pleasure to welcome Professor Kevin Buzzard from Imperial College London, and he will talk about formalizing Fermat. Thank you.
All right. Well, yeah, thank you to Ilka for the invitation, and thanks to everybody who's there online and in person. Uh, so let me talk about uh, interactive theorem provers, just to explain uh, what this talk is about. So an interactive theorem prover, or a computer proof assistant, this is a programming language which is rich enough to understand, you know, logic. Uh, So what exactly do we mean by that? I mean, in a traditional programming language, uh, you have variables, and you can set the variables to be things like sort of floating point numbers, or or strings, or things like this, or real numbers, integers. But in a and so in maybe in a more mathematically uh, sort of a more mathematical programming language might be a computer algebra package like GAP or Maple or Mathematica, when you can say, let G be this group, let G be this specific group. But you can go one level more abstract in an interactive theorem prover. You can say things like, let G be a group, let G be any group, or you can have a variable that represents the statement of a theorem or the proof of a theorem. So that's uh, so they're programming languages, but they're somehow expressive enough to understand abstract mathematics. And there are many examples of programming languages, and Lean is one of them, and Lean's the one I'm going to talk about. But there's Rock. There's much old Rock and Isabelle have been around for decades, and Agda and MetaMath and Whole-Light, and there's many other programming. There's many other interactive theorem provers, and they've been studied for a long time. The earliest ones were around in the 1970s. And now I'm supposed to give you a demo. So let me, there you go. That looks like something completely intimidating. So let's not have that demo. Let's find a new, here we go. Right, this will do. Uh, let's do a demo. So let me prove a theorem about topological spaces. So let's let X and Y and Z be topological spaces. Topological space X, topological space Y, topological space Z. So that's a way of saying, you see that I just said, that just says let X, Y, Z be topological spaces. And let's say F and G are functions. Let's say let F from X to Y and G from Y to Z be functions. So that's F from X to Y and G from Y to Z. And my claim is if F and G are continuous, then so is G composed with F. So that's now a theorem. I mean, maybe I won't prove it. Maybe I'll just example. So that's sort of a hypothesis on F that says F is continuous, and a hypothesis on G that says G is continuous. And then my conclusion is that following function is continuous G composed with F. There, and then I can put sorry here, which is, oh, I've got my, sorry about that. There we go. There. So now you can see what happens. So this is let's get rid of that. Let's make everything a bit bigger. There we go. And let's put this here, and let's put that there. And now you can see the game, right? So this stuff here, this is kind of gobbledygook. But this stuff on the right here, this is something that we can kind of understand, right? So, well, you can see that we've got X and Y and Z are topological spaces. We can see we've got a function from X to Y and a function from Y to Z. This is the current state of Lean's brain, right? And we have these hypotheses that F and G are continuous, and then we have this funny little logic symbol there, that sideways T, and everything above that funny little logic symbol is the hypothesis, and everything to the right, that's the conclusion. So that's what we want to prove. We want to prove that the G composed with F is continuous. And so now we could we could prove this the way we could prove this the way we prove theorems to to the undergraduates. We could what could we do? We could write continuous def, right? Let's let's um let's rewrite continuous def everywhere. So I just typed in a line of gobbledygook, but then Lean's brain has changed, and what's happened? I'm going up and down, so you can see there's before and there's after. So now you see instead of this hypothesis saying this function is continuous, it says for all subsets of Y, if it's open, then the preimage is open. And this is for all subsets of Z, if it's open, then the preimage under G is open. And we have to prove that for all subsets of Z, if it's open, then the preimage under G composed with F is open. So that's great. So let's say, let's let U be an open subset of Z.
Kevin, can you open please your sorry.
What have I done?
I muted you all. I muted all participants, but sorry for including you. Now it's fine. But sorry.
All right. No. Okay. Understand. So you can see me writing code, right?
Indeed, there is no problem.
Okay.
Perfect. Thank you.
So now let's let U be an open subset of Z, and now you see these are now in the hypothesis, right? U is a subset of Z, and HU is the hypothesis that it's open. And what we want is we want the GF inverse of U is open. And what's the proof? Well, first, let's let V be the preimage of U under G, right? Let's do that first. So let's let V. That's a subset of Y, and that's going to be G inverse of U there, and then I claim that V is open because G is continuous, U is open and G is continuous. So have HV is open V, right? V there. And now I've got two things to do, right? I've got my original thing. I've got to prove that this original goal here, but we've also got this other goal. I'm claiming that V is open. And why is V open? V is open because G is continuous. So we could apply the fact that G is continuous. And now when we apply that, it says, well, okay, you can apply that, but you need to prove that U is open. But actually proving U is open is easy because that's this hypothesis here. That's an assumption. So we could do assumption there. And now that's done. You see, now I've got this new hypothesis that V is open. So you see, you just go on like that, right? So now let me just try and finish it in one line. So this is exactly the fact that F is continuous and the fact that V is applied to V and the hypothesis that V is. So I'm just going to cheat. So there we go. So that's the end of the proof. And now you see that Lean's brain has changed. Now it says there's no goals left, right? You see, if I put my cursor up a line, it says I've got one goal, and that's the thing I was trying to prove. So now I get to the end, and it says I've got no goals. So I've proved a theorem, and now I've got this little tick here that wasn't there before. And that little tick there in the margin means I've proved the theorem. So that's what it looks like to prove a theorem in practice. And of course, you might think, well, if it takes that long to prove that if it takes that long to prove that the composite of continuous functions is continuous, then clearly this isn't going to scale. But of course, this is the proof. That's the proof that we teach the undergraduates. You don't have to give it that proof. We could another proof would be there's a fancy tactic that tries to prove that things are continuous. So let me try this continuity. There we go. So the continuity tactic has proved that. You see, I've got another tick here. So there's a much shorter proof that the composite of continuous functions is continuous. We're just using a sort of an inbuilt strategy that knows lots of ways of proving things are continuous. And this is a very easy. We can prove things like sort of sine of x squared plus 5 is continuous. Another way we could prove it. This is such a standard fact. The composite of two continuous functions is continuous. We could do exact question mark. and that searches through the entire maths library, trying to find the proof. And so there you go. There's the it succeeded, and it found lo and behold, there was already a theorem in Lin's maths library, continuous.comp, and continuous.comp, unsurprisingly, says that if f and g are continuous, then so is the composition. So you see, there's all manner. I mean, there's all manner of ways that you can prove that the composite of two continuous functions is continuous. So that's what it looks like using this software in practice. You can either spell things out directly from the axioms, or you can go super fast and you use shortcuts. So there we go. These things, they know the axioms of maths and the rules of logic. They don't know any mathematics, but if you import a big mathematics library, then suddenly they know a whole bunch of mathematics, and then you can take it from there, right? So you can see, in theory, we have all the ingredients for understanding an arbitrary piece of mathematics, right? But of course, in practice, it's not quite as easy as that, especially if the mathematics is very complicated. So that's kind of where we are. And formalization of mathematics, which is the area I now work in, this is the art of taking mathematics, which is written in a human language, and translating it into the language of an interactive theorem prover. Right, so I'm going to talk. This talk is about, or at least to a large extent, about what happens if you try to translate a proof of Fermat's last theorem into Lie. So, which might sound like a sort of a crazy idea. So Fermat's last theorem is this sort of well-known thing. It was open for 350 years. A, B, C, and n are positive integers, and n is bigger than 2, then a to the n plus b to the n can't equal c to the n. That's the claim. And as I say, it was open for 350 years. It was proved by Wiles and Taylor-Wiles in the 1990s. And the Wiles and Taylor-Wiles papers were only about 150 pages, but of course they had many, many references. And so you have to prove everything in that. If you want to do it in a system like Lean, you have to do everything from, you have to start at the complicated proof and unravel it until it's just applications of the axioms of mathematics. So if you were to write that out in full, that's of course several thousand pages. So this is a gigantic project. And how does one go about proving such a theorem in a theorem prover? So at the end of the day, what this boils down to is you have to write a lot of code, right? Or you have to somehow get a lot of code written. Maybe you can get AI to write some code. But another question is, where do you even start, right? And one thing you can do is you can say, well, okay, we've got the axioms of mathematics, so maybe the first step should be let's make an undergraduate degree, and then let's start making graduate courses. Let's build up from the basics, and do it like that. So that's one thing you can do. You can go bottom up. And what does bottom up look like? That means building an undergraduate library, then formalizing graduate level textbooks until all the basics are in place, and then you can start formalizing the difficult research level papers. But one nice thing about this is that another thing you can do is actually you can go top down, where you can just kind of start at the top, and you can try and prove Fermat's last theorem, assuming some other very hard theorems, and then you can try and prove those other theorems, assuming some slightly easier theorems, and then keep going like that. And then what happens? Is you start off with a statement that's very elementary to state. Fermat's last theorem is very easy to explain to Lean, but when you start going down some layers, then you run into more complicated theorems about elliptic curves and modular forms. And then even stating these theorems becomes more complicated. The theorems are strictly speaking easier to prove because you prove them on the way to proving Fermat's last theorem, but they're much harder to state. So that's, so there are your two choices. And of course, we've got to do everything, right? So I've been thinking about both bottom up and top down. And the big problem with the bottom-up approach is that you have just an incredibly large amount of things to do. But fortunately, people started on doing this work in 2017. So we've been at it now for nearly 8 years, just building a sort of a solid base on which we can use to prove not just Fermat's last theorem, but to sort of prove arbitrary projects in mathematics. To basically get sort of a solid undergraduate degree, a basic graduate level definitions and basic theorems, which will enable us to not just prove Fermat's last theorem, but to prove lots and lots of other theorems. So that bottom-up approach is Lean's maths library, MathLib, which was born in mid-2017 and is now 2.25 million lines of code and expanding very, very fast every day. So every day there's typically 20 or more pull requests merged into Lean's maths library. So it's constantly growing. So this is not a part of the, I have a project to prove Fermat's last theorem, but Lean's maths library is not a part of that project. This is just an independent thing with its own legs. It's a free and open source mathematics library, which I happen to have been involved in the development of for a long time. But many, hundreds of other people are also involved in this. So this is nothing to do with me personally. It's just a library that we could never prove Fermat's last theorem without. So it basically by now has essentially all of an undergraduate degree. And it has sort of graduate level topics such as elliptic curves and modular forms, which are used in the Wiles and Taylor-Wiles proof. So very basic facts, about these basic number theoretic algebro-geometric objects are just slowly but surely appearing in Lean's math library. For example, last week we got the proof modular forms form finite dimensional vector spaces. And it's not at all obvious that these spaces are finite dimensional. But we got the proof that we got even a formula for the dimension of the space of level 1 modular forms last week. And we'll get formulas for general spaces of modular forms in the near future. So that's the kind of, that's sort of the boundary of the maths library, sort of basic facts about modular forms that you sort of learn in a graduate course on modular forms. So this maths library just grows, right? It's just constantly growing. We are constantly reviewing pull requests and merging them, which is the way that open source projects grow. And it grows sort of in random directions. It grows like people decide to contribute something and they contribute it and it gets reviewed and it gets merged. And then the library grows. So I personally would like it to grow in the directions that I need for Fermat's last theorem, but other people are growing it in other directions because there's other people doing other projects as well. They're proving other things, across mathematics. So it just grows. It just grows organically. So this is the library that powers the Fermat's last theorem project, which is a different open source project, but it's powered by Lean's maths library. It's downstream from Lean's maths library. And you see, I want to make the maths library grow in the directions that I want, and so that's kind of my job to encourage people to make that library grow in the directions I need. So here's an example of the way that might work. So let me show you the blueprint. So this is some. Oh, I shouldn't have done that. Let me this is some human readable. This is human readable mathematics. So this is stuff. This is just regular mathematics. We like to do everything in the right generality. So I need Frobenius elements. And I thought that Frobenius elements worked for Galois groups of number fields. But if you look in Bourbaki, which is Bourbaki's algebra is an incredibly general text, and it gives you the correct generalization of Frobenius elements, where you just have a finite group acting on an arbitrary commutative ring with no hypotheses, and A is the subring of invariance of this ring. And then we prove this theorem, and you can this theorem has been, I guess we can see probably in does this work? There we go. So there's there's a Lean statement that corresponds to that mathematics statement we were just looking at, and you can go to the source and you can see that there's some Lean statement and proof which correspond to this mathematics we were looking at a few minutes earlier. So I wrote a lot of this mathematics in natural language, and then I said to the community, right, I've written down the proofs that I think we should be translating into Lean. Who wants to help? And then, of course, people just join in and help. And I think if we if I we can probably have a look at the graph. Where's my graph? Let me go back to the oh, here we go. There's the chapter 8 graph. So there's the, you see, these things all used to be blue, and blue meant haven't proved yet, and then they were slowly proved by various people, and when they got proved, they went green, and then this main theorem eventually became green, and so now that's in the FLT project, but that's not really where we want it. We want it in Lean's maths library, and so what happens after that translation process from English into Lean has taken place is that then this code then gets upstreamed to Lean's maths library. And then when it's in Lean's maths library, then everybody who's relying on Lean's maths library, which is essentially everybody doing mathematics in this space, can then access these theorems about Frobenius elements. So that's what it looks like when you're building bottom up. And it's you occasionally run into problems, right? There's two things that happen when you're doing this kind of thing. You find new abstractions and you run into problems. And so we're writing a paper that doesn't explain the mathematics, which is all completely standard. We're just writing a paper explaining the new abstractions and writing the problem. So let me just give you an example. Let me just explain that it's not easy, right? Let me explain one example of a difficulty we ran into where we were proving theorems about Adele's, which is this crucial mathematical structure that we need in order to prove Fermat's last theorem, because we need to talk about automorphic forms, which are functions on adelic groups. And the way this works is that you need Lean to just know really quickly that if you start with a complex structure like a normed field, then you just need Lean to know instantly that a normed field, it's a topological space, it's an abelian group under addition, it's a topological abelian group, it's a multiplicative monoid, and multiplication is continuous. You need to, all of these things, you see what's happened is you have a normed field like the real numbers, and then you want to use theorems about normed fields, but really many theorems about normed fields are not actually theorems about normed, like A plus B equals B plus A. That's a really important theorem about normed fields, but that's really a theorem about abelian groups. And so you apply this theorem about abelian groups, and then the system has to quickly check that every normed field is an abelian group. And so it knows that the theorem, it knows that you can apply the theorem to normal fields. So there's all kinds of things happening behind the scene that, as the end user, you don't see, you just expect it to work. But here's an example of the problems you run into with this system that just makes everything work. If you take the tensor product of two commutative algebras together, tensor B, this admits a map from A, and so it's an A algebra, right? So I've got two R algebras, and I tensor them together over R, and I tensor them together, and the tensor product is an A algebra, and it's also a B algebra. And this automatic system that's doing everything automatically and not troubling you, it knows that A tensor B is an A algebra, but it doesn't know that A tensor B is a B algebra. Not automatically, anyway. And the reason it doesn't is because if A equals B, then you've got some problem, because A tensor A is an A algebra in two different ways, and things are only supposed to be algebras in one way, but that's part of the way the system is designed. And so A tensor A, we only want it to be an A algebra in one way, so we let A act on the left. And that means that you can't let A tensor B be a B algebra. Except you can just override it. You can let A tensor B be a B algebra, but you have to explicitly override it, which just sort of switches on. And then you have to be super careful to make sure that A is never equal to B, because then you'll have some ambiguity. So you're sort of, the system isn't doing everything automatically. Sometimes humans are sort of good at seeing what's going on, but they're actually sort of using things which should be dangerous in other situations. So they can't be turned on in general. And another example is, if M is an A module and N is a B module, then M cross N is an A cross B module. And again, this is just the kind of thing that you have to be sort of super careful about, because sort of A cross A is an A cross A module. And so A cross A cross A cross A will be an A cross A module in sort of lots and lots of different ways. And if you just turned on all these things and made the system do it automatically, it just might make the wrong choice. It might make the choices that not everybody is happy with. So you turn this on globally and other people's code will break. So you just have to, so sometimes you're sort of switching things off and on to make your code work. that ideally you wouldn't have to do, but sort of for sort of complex reasons, it's sort of the sort of thing you have to end up doing. So this is what happens when you formalize mathematics. You'll sort of you have to learn how the system works, and sometimes the system won't do things you want to do automatically, and so you have to sort of tinker. You have to tinker with things, and then it will do it automatically. So there was an issue that we had to just be careful. But another thing that you do when you formalize is that you're forced to find abstractions. You're not forced, but you're encouraged to find abstractions. So, for example, 150 years ago, people were into matrices, but then this abstraction, the idea of a linear map, there's an abstraction of matrix, and that abstraction, gives you advantages. So sometimes you don't have to do calculations of matrix entries. Matrix multiplication is associative, but that's a calculation. But sort of composition of linear maps is associative, and that's obvious because a linear map is a function. The moment a linear map becomes a function, then different abstract, different ideas are available to you. So sometimes you can prove theorems about matrices by proving them about linear maps, and then just choosing a basis at the very end. So abstractions make calculations easier, and so calculations are just the kind of thing that you get really bogged when you're doing mathematics from the axioms. You can get bogged down with calculations. You want to do as few calculations as possible. You want everything to be sort of abstractions and easy to reason with. And so when you're formalizing mathematics, you're really encouraged to find the right abstraction. And also because it came up in the formalization, just let me show you an abstraction that we ran into when we were thinking about Fermat's last theorem. So we want to do automorphic forms over variants of GL2. We want to do automorphic forms over quaternion algebras. So we ran into questions about quaternion algebras. So here's the most famous quaternion algebra, the Hamilton quaternions, four-dimensional space over the real numbers. And Lee knows about the quaternions, but it didn't know that the units of the quaternions were a topological group. It didn't know that multiplication and inversion were continuous. So why are they continuous? They're continuous because they're obviously continuous, because you think about the formulas for multiplication and inversion, and they're not doing anything bad, right? they're addition, subtraction, multiplication, and division, and all of those things are continuous, and so everything's going to be continuous, right? It's clearly these things. It's obvious that these things are continuous, but you can't just tell the system, well, it's obvious, right? The system wants to know why it's true, and so you have to think about why it's true. So why is it true that the units and the quaternions are a topological ring, a topological group? Well, the units of a topological ring are a topological group if you put the right topology on the units. And so we just need to prove that the quaternions are a topological ring. And the way you prove quaternions are a topological ring, you say, well, we can choose a basis. The quaternions are just R to the 4, right? So we choose a basis, 1ijk. And now you think about the formulas that represent addition and multiplication. They're just represented by matrices, right? The addition is a linear map, H cross H to H. Multiplication is a bilinear map, H cross H to H. And all these things are somehow encoded by matrices. And what's the formula for addition and multiplication of matrices? Well, if you think about, that 4x4 matrices, what happens when you multiply two 4x4 matrices together? You're just adding and multiplying the entries, which we involve addition and multiplication on the reals. And Lee knows that addition and multiplication on the reals are continuous. And so you expand everything out, and this is bound to work, right? And you will end up with a proof that addition and negation and multiplication are commutative, right? And that's exactly the kind of thing that you don't want to be doing. Because now suddenly I've turned something which you would never need to explain to a mathematician. You say, well, the quaternions are a topological ring. They're R to the 4, put the obvious topology on. Obviously, they're a topological ring. And now all of a sudden, this proof is an absolute hideous, a hideous case bash of the explicit 4x4 matrices. That's absolutely the kind of thing you don't want to do, right? You want the proof to be one line long. And even if you did it, you see, one thing you could do, you could ask like a language model to prove that theorem for you. And probably nowadays the language model would do it. But it's not the theorem you want to prove, right? Because when we finish doing quaternion algebras over the reals, another thing we need to Fermat's last theorem is quaternion algebras over the p-adic numbers. right? I need to, for a quaternion algebra over the p-adic numbers, I want the units of that to be a topological group, okay? And clearly the same proof is going to, right, exactly the same proof works, right? Because a matrix over the p-adic numbers, you know, multiply matrices over the p-adic numbers, it just involves addition and multiplication for the p-adic numbers, and the p-adic numbers are a topological field, so addition and multiplication are continuous, right? But you don't want to prove that some quaternion algebra is a topological ring and then prove that another one is. You want to find the right theorem, right? You don't want to keep proving similar theorems. You want to prove one theorem, and you prove that one theorem, and then you get all these things for free, right? That's what you want to do. You want to prove the right theorem once. And so now, of course, the question is, what is the right theorem, right? What's the correct generality that this theorem holds in, right? And one issue is that here's something that comes up when you're trying to work out what the right theorem is. The quaternions have got an obvious basis. The Hamilton quaternion is 1ijk. But if you just take a random quaternion algebra over a random topological field, then the axioms of a quaternion algebra just say, well, it's four-dimensional. It's four-dimensional, the center is the field, and it's got no non-trivial two-sided ideals. That's the definition of a quaternion algebra. So it's just abstractly four-dimensional. So what's even the topology on this quaternion algebra, right? I mean, I know it's four-dimensional, so I can just pick a basis. I'll pick a basis, and now my quaternion algebra is isomorphic to ground field to the power 4, and the ground field's got a topology. And so ground field to the power 4's got a topology. I can just multiply, product topology. And now D is isomorphic to K to the 4, so I can just pull back the topology, and that's great. Now I've got a topology on D. But I chose a basis, right? So what if I choose another basis? Then do I get a different topology? Well, again, you think about that. You choose a basis for a vector space, then you choose a different basis, then you've got a change of basis matrix, right? We teach it to the undergraduates. You change the basis, you're just multiplying everything by a matrix. And so I'm multiplying everything by a matrix, and multiplying things by matrices is a continuous map, because matrix multiplication is just addition and multiplication of the ground field, and the ground field addition and multiplication are continuous. And so again, so that's great, right? That means that the topology is independent of the choice of basis, and the proof is 20 lines long. All right. So we don't want to do this. I don't ever want to be dragged in to having to do explicit matrix multiplication and start reasoning about matrix entries and saying, well, they're just finite sums of addition. You don't want to do that, right? So what must be going on is that if I've got a finite dimensional vector space over a topological field, then maybe this vector space has got some kind of canonical topology, right? It's got this canonical topology, and this topology is we get to choose a basis, and then we give B the product topology, and then we prove it's independent of the choice. Okay, so finite dimensional vector spaces over topological fields seem to have some kind of canonical topology. So what's the right question, right? What's the generality? What's the right theorem? So here's the most naive question. Let's say we've got a topological ring, right? Because I never use division. Multiplication of matrices never uses division. So let's say I've got a topological ring, and I've got a module for that topological ring. So R's got a topology, and R is acting on M. Then does M get a topology, right? Is that what happens? Does the topology of R somehow map forward and give me a topology on the thing R is acting on, right? And then here would be a dream theorem, right? Imagine you've got two R modules. R's got a topology, and I've got two R modules. And then maybe these two modules both inherit a topology. And then is it true that maybe every linear map is automatically continuous for that topology, right? Then you would never have to prove that. Do you see? Then you don't have to prove that addition is continuous, because addition's a linear map, right? You get continuity for free. You never have to unravel anything, right? So that would be a dream. But is that true? Do I need that R is complete somehow? I vaguely remember theorems about topologies on finite dimensional real vector spaces being canonical, but somehow the proof involved the fact that the reals were complete. But complete means you've got a metric, maybe. What exactly is going on? So it turns out that this is true. You've got a topological ring, then any module for the topological ring inherits a topology. And so the reason it's true, I asked this question on Math Overflow, having discovered that this was the right question. And 2 hours later, Will Sabin, this guy from Princeton, just said, yeah, that's yeah, here's the topology. What you do, there's a theorem hiding here. What you do is you definitely want addition to be continuous, and you definitely want the scalar multiplication to be continuous. Okay, so M should have a topology that makes those both things continuous. And you just take the finest topology that makes both those things continuous. And it's not obvious that that topology exists, right? I could have like two completely different topologies making those things continuous, and then you kind of like take the topology generated by them, and then maybe addition isn't continuous anymore because you're changing the topology on both sides. So, goodness knows. So you have to prove a theorem that there is a finest topology making these continuous, and that theorem turns out to be true. And if you know it, once you know it's true, you get the hang of proving theorems like this, then it's just a few lines long. And then you prove other theorems, and then eventually you prove this theorem that if R is a commutative topological ring, and then we have an R algebra which is finite as an R module, it could have torsion. It could be all sorts of things. But if you have a module finite R algebra and then you give it this module topology, then A is automatically a topological ring, and you don't have to check anything, right? So that's the theorem you need, and you prove that theorem once, and then you apply it, and all of these quaternion algebras are now automatically topological rings, so they're units of topological groups, and all these facts I needed are all just proved by one theorem. So that's finding the right abstraction, and that's what we prove. So you can get sucked into finding the right abstractions and kind of like going through the proof of Fermat's last theorem and all the references and asking yourself, is this the right lemma? Is that the lemma we should have proved? What's the correct lemma? What's the most general lemma? Start asking these questions, and then of course it will take forever to prove Fermat's last theorem. And indeed, the reason I'm working on Fermat's last theorem is because in 2024 I got a grant, and I argued that if I had 5 years to work on this, then I wouldn't necessarily prove it from the axioms of math. I would just reduce Fermat's last theorem to theorems which were known in the 1980s. So that's not proving all of Fermat's last theorem. I reckon it's between 10 and 15% of the full amount of work. It's sort of that, or maybe a bit less. I don't know. Maybe it's 10, maybe nearer 10%. It's not completely clear. Maybe it's under 10%. But the thing is, there's also a lot of work going on, with the maths library as well. So then you can sort of step back and say, okay, so that's my project, just doing the Wiles and Taylor-Wiles papers. But if that's only, at the end of the day, we've only done 10% of the work, how, now we've got to prove 10 theorems that were known in the 1980s, right? Who's going to do them? Is that going to be like another 50 years? So that's a fair question. And of course, and 2 years ago, that was a completely reasonable question. 2 years ago, it wasn't at all clear what to do, but things move fast in the AI world. So you kind of think, well, maybe AI can help, right? So I've spent half the talk, well, over half the talk, talking about Fermat's last theorem. I'm going to spend the last bit of the talk talking about auto-formalization. So that's a process of getting not humans, but getting a machine to translate mathematics into a formal language. And 2026 has been the year of auto-formalization. We've seen incredible advances. So let me just show you some examples of what's been happening in auto-formalization, and that will make it feel like auto-formalization is completely solved. And then I'll just finish by explaining why it's not completely solved. So in 2025, it started. People took some LLM generated solutions to Erdős problems and got a machine to auto-formalize them. But in January 2026, a lone researcher working at a university, he's an academic like me, he just took a standard ChatGPT Pro account, is $200 per month ChatGPT Pro account, and then gave it an undergraduate textbook and asked it to see what it could do. And it formalized a huge chunk of this undergraduate textbook. And it wasn't in Lean, it was in another proof system called Megalodon. And that's particularly interesting because Megalodon is quite a new proof of system, which only has a very, very small library. So you can't really train, you don't have a lot of good training data, but it turned out it's still enough. You don't need a huge amount of good training data. You can just throw a $200 a month ChatGPT Pro account at this thing here, and it will formalize standard undergraduate theorems. So it wrote a 3,000 line long proof of Eurozone's lemma, right? And if you know some undergraduate topology, you'll know firstly that Eurozone's lemma Eurozone's lemma is not difficult, and it probably shouldn't take 3,000 lines to do. But if you know something about formalization, you'll also know that 3,000 line long proofs are a disaster. What you want is 300 10-line long proofs. You want to break Eurozone's lemma up into lots and lots of small pieces and formalize them instead of just running at Eurozone's lemma and doing it from scratch. So in January, people were saying, well, clearly this isn't going to scale because the last thing we need is a 3,000 line long proof of Eurozone's lemma. But then things move on, right? In February, the new Claude Opus came out, and Claude Opus turned out to be really good at formalization. So in late February, something really groundbreaking happened. Math Inc., who were a small tech company, they formalized some of the work that won the Fields Medal in 2022, Vysotsky's work on 8D sphere packing. So things happened here, right? There were humans that were working on this already. Sid Hariharan was manually formalizing the results, and he had written the blueprint like me. He'd started when he was a master's student in London, and now he's at Carnegie Mellon, and he'd written this blueprint like the Fermat's last theorem blueprint. He'd carefully explained exactly how he was going to formalize this proof. And he put the blueprint up on the internet, and the tech company realized that if they downloaded the blueprint and gave it to an auto formalization tool, then it could just finish the job. So that was kind of spectacular. But even more spectacular was that Vysotsky and co-authors found the best way of putting 24-dimensional spheres in boxes as well. And there was no blueprint because Sid had just been working on the 8-dimensional case. So the 24-dimensional case, they just had the paper. So then they fed the paper to their machine, and lo and behold, 1 week later, 200,000 lines of code later, or a couple of weeks later, we don't quite know. It's all closed source, so we don't quite know the details. It ran 200,000 lines of code, and it had proved that the best way to put 24-dimensional spheres into 24-dimensional boxes is put them at the vertices of the Leech lattice. And this was a hugely disruptive piece of work. And there were really different reactions in the Lean community. So some people were very excited, some people were very angry, some people were very worried that, it was all sorts of things happened, right? This is exactly what happens when AI comes along and disrupts an area. We had this thing going for 8 years. We were just manually formalizing things, and we were fine. You could just leave us to it. We would slowly but surely do it. But now suddenly AI can do it, and the community has to work out what's going to happen next, right? So that was February. In March, Meta, who were a gigantic tech company, Meta formalized a 700-page textbook. And they didn't do the exercises, but they're claiming they did over 500 pages of it. And they did it in 1 week, and it cost them a high 5 figures, sort of 90-odd thousand US dollars. And they used 13,000 Claude Opus agents. And so that's $300 per theorem, or $200 per page, right? And if you think that's a lot of money, then actually, if we were doing that the old way, just getting humans to do it, then it would cost more. Because it would take several person years to do it, and you've got to pay the humans, right? So, of course, the big challenge here is trying to get 13,000 AIs to all sort of talk to each other instead of all doing the same thing, right? But that's just the kind of thing that Facebook can do, right? So why are tech companies doing that? Well, that's sort of an interesting question, because I've been arguing that formalization of mathematics helps us find errors in the literature, helps us find new abstractions. And all of these tech companies, all they're just doing is translating the literature, right? They're not doing anything. They didn't find any errors. There weren't any errors. They weren't going to find any errors in a graduate textbook because the graduate textbook had been well written. And they weren't going to find any errors in Vysotsky's work because the human, we checked it. We gave her a Fields Medal because we knew there weren't any errors. Right? No new abstractions were found because it never thought about the best thing to prove. It just proved what was in the, AI could just blast through things. It didn't think, is this the right theorem? It's just like, well, that's what the humans say. Let's prove it, right? So what's the point? What's the point of these tools that also formalize things? Well, the point is that we've got LLMs writing mathematics, right? We've got these AI slot papers, and these papers are getting better and better. AI is generating mathematical papers written in English, and they're getting more and more, they look good, but they're not perfect, right? They're not even at human standards yet. They're vague, they make mistakes, and maybe we can use these auto formalization tools to check LLM generated mathematics. So I won't talk about first proof because I realize I've only got 2 minutes left. So let me just skip first proof. And let me finish. With a little story about definitions. So Lean's math library is written by humans, right? It's written by experts. And when you see a definition in Lean's math library, you see a definition like is manifold, you should be confident that humans have checked that very carefully and sort of believe that if something satisfies is manifold X, then it really will correspond to what a mathematician thinks a manifold is. But one big issue is that mathematicians think a manifold is all sorts of things, right? There's people do p-adic manifolds, infinite dimensional manifolds, manifolds with corners. They do C-infinity manifolds, but some of them might just do Cn manifolds. Humans mean a lot of things when they say let X be a manifold. And all of those things are in Lean's definition of a manifold. Right? So we have the right definition in the right generality, and everything's been carefully checked by humans. And now, what happens if you ask an AI to do a definition for you instead? So Aristotle is one of these AIs that writes Lean code. And I asked Aristotle to define a Hilbert modular form, but I know what a Hilbert modular form is. And I can speak Lean as well. So I asked Aristotle to give me a definition of Hilbert modular form, and it gave a definition that was nearly right. Okay. But the thing about this definition is it compiles, right? You get the ticks. You get those two little blue ticks that say everything's working. Because you see, if you miss out an axiom, then the system doesn't know. If you miss out an axiom in the definition of a ring or something, that code still compiles. It just doesn't compile to the right thing. So Aristotle wrote code that compiles, but it wasn't quite right. It defined Hilbert modular form, but the definition wasn't the usual mathematical definition of a Hilbert modular form. And so I say, oh, no, this is not right. You need to fix this. And then he gave me another definition that wasn't quite right. So I said, no, you've still got it wrong. You need to do this. And then it basically got it right. So you see, we could iterate. We could do humans and computers talking to each other, and we could iterate, and we could get the definition of Hilbert modular form in the end, right? But the problem is we still needed a human expert. I knew what a Hilbert modular form was. I knew what Lean was. And I needed to be in the loop to make that definition of a Hilbert modular form. So now a lot has happened in the first 4 months of this year. And will we still need experts by the end of this year? Nobody knows, right? Because things are moving so fast. Nobody knows. But now, back to Fermat-Starr's theorem, if we can feed in a graduate textbook into a machine and it can translate it, why don't we just feed the proof of Fermat-Starr's theorem in? And the big problem is that the machines are good enough to do a graduate level textbook where all the definitions are either in Lean or in Lean's maths library, or just slightly more complicated than things in Lean's maths library. But when the definitions get super complicated, the machines aren't good enough, right? They're not accurate. They're not accurate with definitions, right? Modern mathematics is full of complex definitions. Let me show you. Here's a bunch of definitions, right? None of these definitions are in Lean's maths library. There's a bunch more definitions. So I have some postdocs who are working on formalizing the statements of the main theorems, all the main theorems published in the Annals of Mathematics since 2020. And 15% we've done. But now all of these definitions, these crazy, a lot of these are basic graduate level definitions, but they are not in Lean's maths library. So we're missing my guess is we're missing 1,000 key definitions to do all of mathematics. And to do Fermat-Starr's theorem, here's just some definitions we're missing. Modular curves, Shimura curves, Shimura varieties. automorphic forms, connected productive groups. These all play a key role in the proof of Fermat's last theorem, and none of them are in Lean's maths library. And when we have them in Lean's maths library, so the problem is some of these definitions depend on other definitions. So it's not just Maths isn't even ready for these definitions, because to make one of these definitions, you probably have to make 10 more definitions. And then when you've made the definitions, you're going to need to, formalize hard theorems about these definitions, and these are going to depend on other hard theorems that won't be in the library. Fermat's last theorem needs a theorem of Mazur. All proofs of Fermat's last theorem need a theorem of Mazur about torsion and elliptic curves. And Mazur's proof is 150 pages. It needs highly non-trivial inputs from the beginning of the 20th century. It needs highly specialized algebraic geometry from the mid-1960s. It needs Néron models. They need abelian varieties. And there's just nothing there. Right? We need complicated definitions. We need complicated theorems that need complicated definitions that need complicated theorems that need complicated definitions. But you go down and you go down, and you have to keep going a long way down until you get to Lean's maths library. So there's sort of a big gap between the kind of formalization we need and the kind of things that's there, right? And building these complex theories, either costs human time. It costs, you either pay humans to do it, or you pay large amounts of money to get machines to do it for you. So you need time and money, right? So going forward, so this is just the end of the talk now. I'm writing blueprint material. What I'm doing right now is I want to just finish the proof. I want to write down a human readable proof of Fermat's last theorem, modulo all theorems that were known in the 1980s. And while I'm doing that over the next few months, I'll be watching the auto-formalization tools getting better. And when that blueprint is ready, then we can start asking questions like, I wonder what happens if we feed it into the tools now? Because then it will be sort of September, but these systems will have got a lot better. So I'm convinced that I'll have written the blueprint and the lean code to reduce Fermat's last theorem to the 1980s by 2029 when the grant runs out. But could we imagine a fully formalized proof of this theorem? Thousands of pages, all typed into Lean. Really, it's very difficult to predict because we know that things are moving fast, but we don't know how much longer they'll continue to move fast. So that's the end of the talk. Thank you very much.
Wow, it's very interesting talk. Thank you very much, Kevin.
Yeah, no problem.
Yeah, it's very nice. Are there any questions or remarks?
I see there's a question in the chat.
Yes, there's also a question and a long thank you message from Professor Ferhat Taş from Istanbul University.
I said that mathematics has to change with the advent of IA. Yeah. Great, you're teaching functional programming. You're doing Lean tutorials. Yeah, okay. Yeah, thank you very much. Yeah, I think that these auto-formalize, once we get here's one thing that will happen. I think auto-formalization will get good, and then we'll start feeding the literature in, and then it will start finding mistakes. And then we'll have to start fixing it. I think mathematics might take a step backwards in a few areas. That will be sort of an interesting phenomenon. So, yeah. Anyway, anything else?
Actually, I have many questions, but I want to try make them short. First question. Actually, just creating these libraries for AI or any like Lean or the others. It seems like for me, it looks like a time matter. I mean, after because you need some time to teach about some class field theory or the other, because in every time you are putting in something in the library, so it seems that it's a time matter. I mean, after some time, it will be good enough. But for instance, from first minute of your talk, a question occurred in my mind. The question is this: so, can you think that for Fermat's theorem or other theorems, Lean can make a proof, an alternative version of the original proof?
Oh, well, maybe AI could do that. I mean, lean is not AI, right? Lean is just checking the proofs.
Yeah. I mean,
Yeah.
I think you
But,
understand my question. I mean, will it be the same proof as Wiles did?
oh, well, the proof, I'm formalizing a more modern proof than Wiles's proof, but I'm still formalizing a proof which is in the literature, right? Right now, I'm giving lectures on Fermat's last theorem, and I'm sort of taking pieces from the literature. I'm writing a modern proof, but it's not my proof. It's not my ideas. It's all Carré and Vandenberger and Kissin and Taylor and lots of other, and Dieulefait, lots of people. But that's me doing it manually. Whether
I,
AI can come up with a new proof, I mean, it's not impossible, but that's not really a lean question.
I
You know,
see.
if AI came up with another proof, it would write it down in English, and then we should get lean to check it.
I
Right?
see. Another question: if you have a very big amount of money, which parts you invest on? AI mathematic tools or mathematicians? By the end of 2030s, let's say.
Now, this is a hard question. Um, yeah, this is a very hard question because right now, I mean, this example of this 700-page textbook, that's an example of AI formalized this textbook, and it was cheaper than getting humans to do it, and it was quicker. So there it's winning. But if I asked AI to prove Fermat's last theorem, it would just wouldn't get anywhere right now, today. But if I ask it again in 6 months, who knows, right? I don't really even want to predict what would be happening in 6 months. So and, and if you want to hire a human, it might take 6 months to even hire them, right? And so it's sort of difficult to it's sort of quite a weird situation. Yeah, who knows? Who knows how much better these things are going to get? Yeah, it might not get any better. We might end up having to do a lot of stuff manually anyway. But I think this is unlikely because there's so much money pouring into it.
I see.
Uh,
And one
yeah, I
last
don't know.
question.
It's
Yeah,
difficult.
one last question about for I'm talking about in job sense. I mean in employment sense.
Ah,
What you expect mathematicians are doing by the year of 2040?
oh, okay. Oh, they'll still be doing mathematics. That won't go away, but they'll just be doing different things. They'll just have very good tools. I mean, it might become the job of the mathematicians to ask the right questions.
So yeah, actually, someone needs to ask some questions. You are right. So some
Yeah.
undergraduate students of mine are already watching. Maybe they have some language problems, but I will explain them later. So sorry, last of the last question. Uh, so what are your advices for the future mathematicians on this aspect?
I think that you should learn how to use these AI tools, but I wouldn't worry too much because I don't think these things, remember, these things are only trained on what we know, right? We've seen very little, we've seen very little AI doing things that nobody knew how to do, right? The most interesting things have been AI human collaborations, right? I don't think I don't think AI is just going to take over
Yeah.
because AI is only trained. Yeah, AI is only trained on what humans know. So can it really start having innovative ideas? Yeah, we haven't. All I'm saying is we haven't seen that yet, right? This software has existed for 4 years since 2022. We still haven't really seen it have breakthrough new ideas that change a field. And will it ever do that? I don't know. So learn how to use it and then collaborate with it because it
I
thinks
see.
about stuff in a different way.
Thank you. You have one more question on chat from Professor Arif Deniz.
Oh, hi. Right. Does LLM-based auto formalization reduce the total human effort? Uh, well, well, the big problem is it doesn't work, right? At the minute. I mean, if it works, then yes. Because if it works, then here's the problem. This is the thing I skipped. I was going to talk about first proof, but then I realized I'd gone on too long. Um, you want to solve something difficult, you ask an LLM, you ask ChatGPT. ChatGPT writes stuff, write several pages of output, but you don't know if it's true, right? You don't know if you believe it. But then so you've got to read it, okay? Because if there's just one thing wrong, then you're in trouble. So the vision is now you take this output and you feed it to an auto formalization tool, and the auto formalization translates it all into lean and says, yeah, this works fine. And if that happens, you still have to do some work, right? But you only have to read the statements. You just have to read the statements of what's been proved. You just have to check that what the lean has proved and what the AI has proved actually corresponds to the thing you want it to prove, right? Because if the name of the theorem is Riemann hypothesis, but when you look at what it says 2 add 2 is 4, then it's very easy to prove that theorem, right? Because it's not the Riemann hypothesis, it's something else. And if the name of the theorem is Riemann hypothesis and it has something that involves zeta function, but then you look at definition of zeta function and it's just constant function, you know, so you've got to be careful. You've got to carefully read definitions, but that's much less work than having to read 20 pages of LLM generated output. So it's absolutely saving human effort. But the problem is auto formalization doesn't work yet, right? It can only do certain things. You know, it will get better, but will it get better enough to do everything? Well, right now it can't even understand everything, right? All these all these theorems in the annals of mathematics that mention these words, Lean can't even understand the statement of those theorems. So we need to work on definitions first somehow. But when all the definitions are there, it should be it should really offer us a huge time-saving opportunity, I hope.
Yeah. Here I have a short personal comment on this question. Actually, I'm also using AI tools, and what I feel, I think it creates some more space for my creative area. I think it's giving me more time to think about some deep questions because, for instance, I'm not putting a lot of time to correcting my codes on LaTeX, especially or writing codes in Magma. It's now or writing functions in Magma or PariGP or Sage. Now it is much more simple. So we have more time to think about some really good ideas. So I'm looking at from this point.
Right, but the way it's very important message is that what you're an expert already, right?
Yeah.
So this is where these tools are most powerful. You're an expert already, and you say, do this thing for me, and then you look at the output and you check that it did what you wanted it to do because you understand it, right? And I'm giving this course on Fermat's last theorem, and I'm just the same. I read something in the textbooks and it just says, oh, this is proved in this paper, and you kind of think, oh, I just want some idea. I don't want to go through. I just want an idea of the proof. Like, how does it work? And you ask a language model, like, can you summarize this proof? And then you read the output and you check it's okay. Right? This is the way to use LLMs. You're an expert, or don't ask it to do the work for you because you can't do it. Ask it to do the work for you because you're too lazy to do it.
Yeah,
and then you get a big speed up.
Perfect. You have a nice conference in July in Norwich. As far as
yeah.
So what is the structure of this conference? I mean, you will just.
Well, I'm not organizing it.
Yeah,
I'll be going.
So
this is LMFDB, right?
Yeah. Yes.
We want to get L functions and modular forms database wired up to Lean, and so we can do examples of elliptic curves. And so there, you see. So the big question is, what are the missing definitions in Lean's maths library? That's one question. Take Shafarevich group, things like this, rank of an elliptic curve, Q expansion of a modular form. Right now, there's people working very hard to get those definitions into place.
Wow.
And then, we can start thinking about examples in at Norwich. Yeah, it should be lots of fun.
Yeah. Thank you very much for having your time. It was really marvelous talk. And you have also thank you message in chat. I believe we don't have any. Are there any more questions?
I should advertise. I'm running a workshop, just a week or two before.
Yes, please.
Yeah, let me advertise my workshop. The week before that Norwich workshop, I'm advertising a workshop in let me put this down here. Uh, here's my advert. Look, I'm running a formalizing format. This is on the link. Let me link to this thing here. Copy link to message. I'll just sit there. There's I'm running a workshop in England the week before this Norwich workshop. So, if you're going to be if you're going to be in England, then you can come to my workshop the week before. And we're going to be thinking about using AI tools to maybe auto-formalize chunks of Fermat.
Wow.
So there you go.
Thank you. Thank you very much for the talk again. And I have just short announcement for the next talk. Next month, for the last talk of this semester, we will host Professor Masanobu Kaneko from Kyushu University. And actually, it will be a farewell seminar for him because he's retiring this month. So it will be very, how I would say, it will be interesting seminar. So you all invited for June talk for Bileşik Algebra and Number Theory seminar. So thank you very much, Kevin, and see you around.
Yeah. Thank you very much.
Bye bye.
Bye bye.